Hello, welcome back. We're learning how to solve systems of equations in algebra. In the last couple of sections, we learned how to solve these systems of equations just by graphing them. We graph them on an xy plane, and we just look to see where they cross. And wherever they intersect is called the solution. And we write that solution down. Just like any solution, we circle it as the answer. If the lines have an intersection point where they cross, then we say it's consistent. But if the lines are parallel, there's no solution because there's no intersection point, and we call that inconsistent. And then we also had the really weird case of dependent system of equations we talked about earlier, and we'll just leave that alone for now. In this section, we're going to learn how to solve these systems of equations to get the answer, the intersection point, but we're not going to graph them. We're going to solve them by what we call substitution. Substitution is probably one of the most used things in algebra. And I told you, and I've been trying to tell you over and over again, how useful these systems of equations are in real life when you get down past algebra a little bit. And that's why we have a million different ways to solve them. So here's just another way. But the end game is the same. We're just trying to find that intersection point. It's just that when we graph these things, it's kind of hard to read the intersection point exactly. Is it 3.444 or is it 3.445? It's hard to read it on a graph, so we want an exact way to do it. So what we have on the board is the very last problem we solved in the last section. I gave you this equation, we put them into slope-intercept form, we graph them, and from the graph we figured out that this is the solution. X is 3.5 and y is negative 0.5. So this is an equation that we've already solved. And we're going to do this a lot. We're going to be solving a lot of these problems. We've already solved them by graphing. We'll be doing them just a different way to get the same exact answer so we can kind of verify that the answers are correct. So here's what we're going to do. Let's take the first equation and I need to get through a couple of problems for you to get the hang of it. So for now, just kind of go with me. Let me take the first equation and let me solve for y, just like we've done many times before. I'll say that y is equal to negative x plus 3. How do we get that? Because we subtract x from the left, we subtract x from the right. So we just moved it around and we made it equal to this. Now this equation over here, I'll switch colors. I'll do the same thing by solving for y. I will say negative y is equal to negative x plus 4. Right? By just subtracting x from both sides. Now we have to divide by negative 1. So it'll be negative x over negative 1 plus 4 over negative 1. So here we have a division. We'll have x, and here we have the minus sign that's going to float up, and it's going to make it minus 4. So we have x minus 4 over here. So in this case, I'm giving you these two equations, but I could have also, in a separate problem, I could have just given you these equations. And I'm going to ask you the question, solve the system of equations. Which means, in your mind, you know that means I'm looking for an intersection point that's common to both. In other words, I want to find the xy value, the xy pair, that works if I substitute it into line number 1, but also works if I substitute it into line number 2. That's what we've said all along. Now notice what I'm saying here. I'm saying that the y values of this line is equal to this junk, and I'm saying the y values of this line is equal to this junk. So if there is a point where they cross like this, then it must be true that because at the intersection point, we know that this is the answer, right? So we know that the y values of both of these lines at this point is the same, because that's what an intersection point is. We intersect them, and we're saying, hey, there's a point here, x comma y, that works for both lines. So if there is a solution to this, which we're assuming there is, then this y value, whatever it is, I'm pretending I don't know what it is, but we actually do know what it is in this case, has to be the same for both of them. So if we're saying that this line is y is equal to this junk, and we're saying that this line is y equal to this junk, if there is a solution, then that means I can take this y and I can plug it into this. Because I'm saying y is equal to this, and here I'm saying y is equal to this. Well, if I'm saying that there's an intersection point, then I have to be able to substitute what this y is equal to into this equation, because I'm saying that these y's are the same. Because if they cross, the y values have to be the same at the intersection point. I'm trying to emphasize that, right? So, because you don't know what it is, but you know what they have to have a common y value, so I'm going to take this y value from this equation, and I'm going to stick it in here. But I know that this y value is actually equal to this. So I can take this, what it's equal to, and I can stick it in there. So what am I going to get? Well, I'm going to get the following. I'm going to say, I'm going to work over here. This is what y is equal to, negative x plus 3. But it's got to be equal to this. x minus 4. It is absolutely crucial that you understand why I'm doing this. It's because I'm saying there's a common intersection point here. So wherever they cross, the y values have to be the same. So I can substitute y into here, just like any variable can be substituted in, right? But I know what y is equal to. It's equal to this expression for x. So I'm just putting it on the left-hand side of the equal sign because that's where y is. So I just literally stick it in for y right here. Just as it sits, x minus 4 on the right, this stuff on the left. And then the magic can happen. I can now solve for x. Right? I'm going to move x to the left. So I'm going to have negative x minus x plus 3 is equal to negative 4. I just subtracted x from the right, subtracted x from the left, which becomes negative 2x plus 3 is equal to negative 4. Now I have to solve for x, so I'm going to move 3 to the other side. Negative 2x equals, I'm going to subtract 3. So what is negative 4 minus 3? Negative 7. And then finally, to get x by itself, it's just going to be negative 7 over negative 2. So then x is going to be the positive. It makes it positive. I can't really do this division without introducing a decimal, so I'm just going to leave it as 7/2. So I'm saying the x value of the intersection point of these graphs is 7/2. 7/2. 7/2. If you get a calculator out and you put 7 divided by 2, what are you going to get? 3.5. What we found was we haven't found the whole solution yet, but we found that these lines intersect in a place where the x value of the intersection point is 7/2, which is 3.5, 3.5. All right, so now we have half the answer. This is half the answer. How do we find the other half the answer? Well, look at what we were given. We have two equations. One of them is y is equal to negative x plus 3. The other equation is y is equal to x minus 4. And now we're saying that we know what the x value is. That's the solution of this guy. So if we know this, we should be able to stick this value into this equation, or we can stick it into this equation. Either way, we should get the corresponding value of y that works. So let's take this, and I'm going to try to do it with little lines to help you. So I'm going to go ahead and say here, when you see me write something like pi, that means plug in, right? I should have written it here also. Pi, that means plug in for y. This means plug in for x, right? So let me go over here, and now we're saying that the corresponding value of y is equal to x, but we now know x is 7/2 minus 4. Now I'm sorry, sometimes in math you just have to deal with fractions, and it's not fun. I mean, I agree with you, it's not, but this is what it is. So this means that it's 7/2, and this is 7/2 minus 4 over 1. It's easier to write it like this, right? Minus 4 over 1. How do I get a common denominator here? I have a 2 and I have a 1, so I can just multiply this by 2 on top and bottom. And that means what I'm going to get for the y value is 7/2 minus, on the top I'll get 4 times 2 is 8, on the bottom I'll get 2 times 1 is 2. And now I have 7, I have a common denominator, first of all, of 2. That just goes on the bottom. And then it's 7 minus 8. What is 7 minus 8? Negative 1. So what do we have? The y value is negative 1/2, which is exactly what we got when we write our graph. So what we write down is the solution is the x value of 7/2, or you can convert to decimal if you like, and the y value is negative 1/2. This is the solution, and you would write down also it's a consistent system, because consistent systems are ones that have solutions of intersection points. It is so incredibly important that you follow what we're doing here. What we did is we said we have two equations. I can take one, because I'm saying they have to be equal somewhere, so I'm going to take the y value of this one, I'm going to stick it into this one. But then when I do that, I eliminate y completely, and I only have an equation to solve for x. When I do the math and I simplify it down, I get the x value that is common to both equations. Once I have that one, I substitute that in to the value for y that will give me the value of y. When I put in the value of x, I do the math there and I get the value of y. So as a pair, it is x comma y as a solution point. Now, you might say, well, I can take this x value and I can stick it into here and get the answer. But what I'm telling you also is that once you have the x value, you have the choice. You can stick it in here to get y, but we're saying that these are equated at that point. So you should be able to take it and also put it in here and get the same answer. In other words, it shouldn't matter once I get down to half the answer which direction I go to get the other. So let me just do it for you real quick. So the solution is done. We've solved it. But now let's take this guy and put it in here. Y is equal to negative x, but x is equal to this, so it's negative 7/2 plus 3, which is negative 7/2 plus 3 over 1. Now it's the same sort of thing. To find a common denominator of 2, I'll just multiply this by 2 and this by 2, which means I'm going to get negative 7/2. And over here I'll have 6 on the top and 2 on the bottom, which means I'll have a common denominator of 2. What is negative 7 plus 6? Negative 7 plus 6 is negative 1. So the value I got for y is negative 1/2 is exactly what I got the other direction. So it's not a magic trick. It's not like going and like somebody throwing cards and like flip the cards. It's magic. You got the same answer. It's not magic. It's because we know that these lines go in different directions, and we know that in all likelihood they're going to cross somewhere. At the point that they cross, the x and the y values of both lines are the same, right? That's why it doesn't matter if I put this into here or here, I'm going to get the same value, because at the point of intersection, the x values of both of these lines are the same. And the y values of both of the lines are also the same at the intersection point. So that's why I can take and substitute in and get the x value, and then go back to either direction and get the corresponding y value. So from here on, I'm not going to tell you, I'm not going to do both of them. I'm not going to put it in here and then put it in here and show you. Basically, you have the choice. Either way is going to give you the correct answer. All right, but you have some freedom in how you choose to go about doing this. Now this is giving you an exact solution. It's giving you 7/2 and negative 1/2. This is exact. By reading a graph, you're not really sure if you're right, because who knows if am I this way or am I that way, but by getting an exact solution, it's exact, and you know exactly what you have. I will say one more thing. As you get down to this point, this is a well-behaved problem, meaning that you get it down, you get a value of x, you put it in, you get another value of y. There's only one answer to this that you're going to get. Sometimes when you get down and you start substituting in, you start getting weird things happen that don't look so well behaved. In those cases, you might have an inconsistent system where there's no solution, or you might even have a dependent system where the lines are basically the same equation, and you have an infinite number of solutions because it's the same line. Both of the equations are the same thing. And as we get to those problems, I will show you how to identify that. I'm not sure if we have any in this lesson or not. Let me just check real quick. Yeah, we have one coming up later where there's no solution at all. But for now, let's go on and move along and try to solve another one to get some practice. Let's say we have the system of equations, y is equal to 4x, and we have the other system of equations, or the other equation, x plus y is equal to 10. Now actually, we've already solved this one also. This is one that we solved by graphing, and so we know already that 2, 8 is the solution. But I'm not worried about giving you that, because if you just circle this on your test, nobody's going to give you any credit. I mean, nobody cares if you can write down an answer. What I care about is if you can do it and show me how you did it, right? So what's the strategy here? The strategy for solving systems of equations by substitution is just to take one equation and substitute it into the other one. Then solve for what you can, get an answer, and take that answer and backward substitute it into one of the first equations to get the other half of the answer. That's pretty much the roadmap for every one of these. So since this equation is already solved for y, what I'm going to do is I'm going to plug it in for this value of y. I'm going to plug it straight in. So what I'm going to have is over here, if I were to work and pull that down here, it would be x plus y, but now I'm saying y is actually equal to this, 4x, is equal to 10. You see how all I did is I took this value and I just stuck it in where it should go. Now what do I have is 5x equals 10. Now what do I have is 10 over 5, because I divide by 5, x is equal to what? 2. So I'm saying the x value of the intersection point is 2, which is exactly what we found by graphing. The value of the guy is equal to 2. Now, or the intersection point is equal to 2. Now, we take this half of the solution, we have a choice. Let's stick it into the easier one. This is the much easier equation to deal with. So I'm going to go over here and I'm going to say y is 4x, because that's what I'm given. So y is 4 times, what is x? We now know x to be 2, so y is 8. And this is exactly what we got here. So then we say, what we know is that 2, 8 is the solution. And we say it's consistent. That was a super easy problem. because the equations were already more or less solved for you in such a way to make it very simple to plug it in and find the answer. But I want to get the point across of how to do it before we get into more complicated systems. Plug in, solve for the first one, take this answer, stick it in, and get the other answer. Now, what would happen if I took this and stuck it into the other equation? I would put 2 in for here. It would be 2 plus y is 8, but then I'd have to subtract 2, which means y would be 8. I would get exactly the same thing if I had put the guy over here into the other one. All right? So let's now take a look at a problem that we haven't solved already once before by graphing. Let's say we have x minus y equals 2x minus 2. That's one equation. And then the other equation is x plus y equals 2y minus 2. So they look similar, but don't be fooled. You have x minus y on the left, you have x plus y over here, you have 2x minus 2 and 2y minus 2 there. So you don't yet know, is this consistent, is it inconsistent, does it have a solution? Nobody can look at this and tell you, oh yeah, I know what that is. Nobody can. If they tell you they know that, then they're not telling you, then they're just fooling themselves. All right, what we have to do is find something in this equation to substitute into here, or I can go backwards. I can find something here and substitute in over here. All right, let's first, I'm just going to pick something at random. Let's just work with this equation, and let's solve it for y, right? Let's just solve it for y, so we'll substitute it back in over here. So what am I going to have? Let's move x over here first of all. So it'd be y is equal to negative x plus 2y minus 2. I just take the x and move it over by subtraction. And now I have a y over here. I need to move him over. So it'll be y minus 2y is negative x minus 2. I just subtract 2y, subtract 2y. Now this becomes 1 minus 2. What is 1 minus 2? It's negative 1. So it's negative 1y equals negative x minus 2. Now to get y by himself, I have to divide by negative 1. So negative x over negative 1 minus 2 over negative 1. Just divide each term by negative 1. And so what I'm going to get for the y value is going to be positive x, this will be positive, plus 2. Right? So I have x plus 2 here. Why did I do all that business of solving for y? Because I have to take something from one equation and solve it, plug it into the other. So that means you have to solve for something initially that you know what it's equal to. I don't really know the answer, but I know it's equal to x plus 2. And then I'm going to stick it into all the locations in the other equation where y is prevalent, or where y is. So what I'm going to do is I'm going to go up here, I'm going to go and say plug in. That's what the PI means. And so what I'm going to have is x minus y, but I'm going to have to wrap it in parentheses because now I know that y is x plus 2. It's important for you to wrap things in parentheses because if you don't, you will make sign errors. You're subtracting the value of y, which is a big expression, so put it in parentheses, equals 2x minus 2. So on the left-hand side, you're going to have x, here you have a negative 1. Negative 1 times x is negative x. Negative 1 times 2 is negative 2. 2x minus 2. Now I have to collect all the x's. But the interesting thing about it is, on the left-hand side, I have x minus x. That's just 0. It goes to 0 right here. So on the left, all I have is negative 2 is 2x minus 2. So just to make it a little easier, let me leave the x on the right and let me pull the 2 over by adding. So what it'll be is negative 2 plus 2 on this side equals 2x. All I did was add 2 and add 2. But on the left, that means I have 0 is 2x. Now, if I want to get x by himself, it'll be 0 divided by 2. So what I've said is that x is equal to 0. All I've done is I've taken something from the right-hand equation, I've grabbed it, I stick it in the value where it goes, and I've simplified and solved everything down so that now that I know what x is equal to, that's half of the answer. Now I have a choice. I can take this value and I can stick it into this equation, or I can take this value and stick it into this equation, one of the original two. Or I could take it and I can stick it into the original one here, but I've already manipulated this one, so this is a much, much simpler place to go. So I'm going to go this way, and I'm going to plug it in here. It doesn't matter which way you go, you're going to get the same answer. So what happens is, you get that y is equal to x plus 2, but now we know that x is 0. Plus 2, so y is equal to 2. So what you write down in your paper is 0, 2 is the solution, and you say it's consistent. Consistent. All right? So if you were to take this value of 0 and stick it in here, what would you get? Well, it would be 0 for here, 0 for here. These two terms would drop away completely. You would have negative y is equal to negative 2. You would divide, so you'd say y is equal to 2, exactly what we got before. All right, so that's a consistent system. All right, so far, if you were to graph this and graph this, you would find they would intersect exactly at this point. If you were to graph this and you were to graph this, you would find that they intersect at exactly this point. If you were to graph this and graph this, you would find that they intersect at exactly this point. And in fact, we've actually solved a lot of those already, so we've already done the graphing for a lot of them. Now what I'd like to do is show you what a set of equations looks like when it's not well behaved, it's not consistent, and kind of like how you identify what to do and so on as we go on down the road. So the system of equations we're going to have for our last problem is 2x minus 3 times y is equal to 2 minus x. And the other equation is going to be 3x minus 2y is negative 2 plus y. All right, now we've already actually solved this set before as well. So if you go back to the graphing methods, you'll find that we've already graphed them. These lines turn out to be parallel, right? So let's go and work through it through substitution and just see what it looks like when two lines don't have a solution because they're parallel, right? So first of all, this equation has a bunch of stuff all over the place, x's and y's, and this equation has a bunch of stuff all over the place, x's and y's. So the first thing we're going to want to do is clean them up. So what I'm going to do here, what I mean by clean them up, is try to get the x's and y's off to one side there. So let's put it in standard form. Let's get the x's and y's on one side. We can do it many different ways, but let's do it this way. Let's move the x over here. So what we're going to have is 2x, we're going to add x, so it'll be plus x minus 3y equals 2. I just added x and I added x, so this becomes 3x minus 3y equals 2. I could put it in mx plus b form. That's totally fine, but let's just do it this way, just to do something a little bit different. All right, now for this guy over here, let's put it in standard form also. Let's move the y over here. So we'll have 3x minus 2y. We're going to subtract y, means we're going to subtract another y, is negative 2. We subtracted y, we subtracted y. Over here, we're going to have 3x minus, what's minus 2 minus 1 is minus 3y. Negative 2 is the answer. Okay, so now we're down to the point where we need to solve for something. We need to solve for something in order to substitute it into the other side. You have many choices on what to do. I can solve for y, meaning I got to move this thing over here, divide by the negative 3, and then when I solve for y, I can stick it into the y value here, and then I can find x, and I can go on from there. Or I can solve for x, actually. I don't have to always solve for y. I can solve for x, meaning I'll move this over here, divide by 3, I'll have an x value, and then I'll stick it into here, and then when I get all the stuff down, I'll be solving for half the solution that way. That's fine. The only problem, it's not really a problem. I'm trying to teach you different ways to, that's of course fine, okay? But you notice what happens sometimes in our very first answer, in our very first problem, sometimes what happens is when you get down and you do substitutions, you get down to where you have fractions. And then you have to plug in a fraction into the other equation and you have to deal with a lot of fractions. Okay, here I'm in a situation where I have to decide what to substitute in. If I solve for x, I'm going to move this over and divide by 3. I'm going to have a fraction over here somewhere because 2 divided by 3 is a fraction. So I'm going to have to, when I plug it in, I'll have to have a fraction inside of whatever I plug in, which means I have a lot of fraction math, all right? And if I decide to solve for y, I have the same problem. I'll move this over, divide by the negative 3. I'll still have a fraction because 2 divided by negative 3 is a fraction. So when I move the y in here, I'll have fractions to deal with. I'll have all kinds of things, which is totally fine. I want you to know how to deal with it with fractions. But in this case, there's actually an easier way. So it's not a shortcut, but it's just something that you can notice. Notice that I have a 3x here, and I have a 3x here. So instead of solving for x and putting x in, let me just solve for 3x. If I just solve for 3x, if I move this to the right, it'll be 3y plus 2. You understand that? You just add 3y, add 3y. Now I have this. But you see, it's perfectly fine to take the value of 3 times x and stick it in to here because I happen to have a value of 3 times x right there. That's perfectly fine. I mean, of course I could solve for x, meaning I have to divide by 3. You see, that's why I'm saying you'd have the fractions. And then the fractions would have to go in here. And that's totally fine. It's just you're going to have to deal with all of the fraction arithmetic to get the answer. But in this case, there's a 3x here and there's a 3x here. So instead of solving for just x or just y, let me just solve for 3 times x. Because remember, whatever x is, it means I can substitute them in. So that means if I can substitute in for x, then I can also substitute in for whatever 3 times x is. Whatever it is, 3 times x in one equation has to be the same as 3 times x in the other equation. So when I plug in here, what do I get? When I plug in here, I'll have 3y plus 2, that goes in here. Then I have the minus 3y is negative 2. I've just taken this value, I've stuck it in right there, minus 3y, here I go. Now, what do I get? I have this cancels with this because 3 minus 3 is 0. So what do I get? I have 2 on the left, negative 2 on the right. That is impossible. There is no way that 2 can ever be equal to negative 2. What this is telling you is it's impossible, so there is no solution, which means they're inconsistent. Inconsistent. All right? This is what this is telling you. If you ever substitute in someplace and you start to get a nonsense answer that's never true, that means that it can't be true. What you've put in there is impossible for the x values to be the same. That's what this is telling you. You put it in there saying, hey, the x values have to be the same at the intersection point. But when I put it in there, I get something completely impossible, that 2 is equal to negative 2 and the variables all drop out. And every other problem, when we substitute it in, we were able to get an answer. When we substitute it in, we were able to get an answer. When we substitute in here, we got completely destroyed. We have no way of proceeding. So at that point, you stop and you say there's no solution, inconsistent. How do you know there's no solution? Because this is impossible. You cannot have 2 equal to negative 2. Now, physically, what it means is that if I solve this in mxb plus form, if I rearrange it, and I rearrange this in mxb plus form, you're going to find that these 2 lines have the same slope. They're parallel lines, which means, as we've talked about in the last section, they're parallel lines and they will never ever cross. So that's why it's impossible for the x values to be the same or the y values to be the same, because they're parallel. Now, we've actually done this problem in the past. If you go back and look at our graphing systems of equations, we actually did this one before, so you've actually seen the graph of this. I'm not going to graph it again. But the point is when you're solving by substitution, you're not graphing anything. So if you don't know what the answer is ahead of time, what you look for is some impossibility happening. You obviously go back and check your math and make sure, but when you get to something impossible, then it's game over. There's no solution, right? I also wanted to impress upon you that you don't have to solve for x or y to sub in. You can solve for multiples if whatever it is you're trying to plug in exists in the other equation, if it's easier. I mean, if I went ahead and divided by 3 and found x, then I would have a bunch of fraction arithmetic to do here, but ultimately it would be the same thing. It would reduce down to something impossible. So if you want to verify that yourself, do that on a separate sheet of paper. In this lesson, we wanted to introduce the concept of solving systems of equations by substitution. It's a little bit of a pain because you have to substitute in, get an answer, substitute in again to find the second half of the answer. But the advantages are that you get exact answers, you don't have to graph anything, and it always works, always. So if you're doing the math correctly. If you get something impossible, it means there's no solution, which means it's inconsistent. So be on the lookout for that. Make sure you can do all of these yourself. Follow me on to the next lesson where we will continue solving equations by substitution, and we'll get practice with other methods of solving linear systems as we go.